Let's talk about floating point numbers and round-off errors. So basically, most computers deal with real numbers in the binary system, so which is in base 2. If you represent a number in base 10, let's say you have 427.325, this is how we can write this in base 10 representation. In base 2, this can be represented as in terms of the powers of 2. So for example, you have 2 to the power 3. So this number, you read this as, so this is the 0th order, first, second, and third power of 2. So you have 1, this digit times 2 to the power 3, and then you have 0 times 2 to the power 2, etc. So this is just an example. You can represent different numbers in base 2 like this. Most computers work internally in the base 2 in the binary system, but they communicate with the user in base 10, which we are more used to. And computers are not able to operate using real numbers with more than a fixed number of digits, because the memory in the computer must be fixed. It is not infinite. So the simple real number, like let's say 1/10, cannot be stored exactly in any binary machine, right? Because this keeps repeating itself, and there's no perfect way. Even if you increase the number of digits here, you will still have some loss of precision because of this finite number of storage that we have. So this brings us to the concept of rounding. In scientific computing, the number of digits in the intermediate results may become larger and larger, while the number of significant digits remains fixed or decreases. For example, you can think about this real number, which has, let's say, 7 digits after the decimal point. But if we have, let's say, just storage enough to store the first 4 digits after the decimal point, this will be rounded to 4 digits because that's the capacity of our storage. Or if you have another number like this, so this will be rounded to 1.000, and similarly for the others as well. So there's some rounding happening because we have the limited or finite number of memory to store the digits of these numbers. So important thing is we need to think about the loss of significance. When a real number x is approximated by another number x star, the error is going to be x minus x star. And the absolute error is the absolute value of this quantity. And also you can write the relative error by dividing with the exact value of this number. So this gives us the relative error due to this possible approximation. So the subtraction of two numbers that are close to each other, for example, think about these two real numbers. Since these are very close to each other, right, x minus y is actually close to 0. And if you round these numbers by this floating of x, float of x, so suppose we have this rounding, and also we have to round the second number. So the difference of these two numbers is approximately, well, it is rounded as 0.0013. So here, if you are considering this relative error, so the true value is x minus y using the exact numbers. But if we are approximating these x and y, and if we are subtracting this, so this includes some error due to the approximation. And if we divide by the true value, x minus y, that's the relative error. So the relative error is, in this case, is quite high, as 4%. So another example, so if you are evaluating this y equals to x squared plus 1 minus 1, so this involves subtractive cancellation and loss of significance for small values of x. Because think about this, if x is very small, close to 0, then this is close to 1. And in other words, you are subtracting this quantity from 1, but these two are very close to each other. So that will increase the potential relative error that you will have. So how to solve this and how to evaluate this in a better way? That's the question. And in order to do this, we can multiply and divide by this term. And by doing this, now we will have some simplification in the numerator. That's going to be just x squared. And we are going to divide by square root x squared plus 1. So this time, instead of evaluating this expression over here, we can actually evaluate this expression, which is equivalent. But in this expression, we will not have the problem of subtracting two very close numbers. Remember, if these two numbers are very close, the approximation or the rounding errors will bring us higher relative error. But in this case, this expression will not introduce a high relative error. So although these two are mathematically equivalent, in the computer arithmetic, the loss of significance or the rounding errors for these two expressions are not going to be equivalent to each other. So this is something that we should pay attention. Although the mathematically expressions might be the same, the rounding errors are not necessarily the same.